Imagine flying to the other side of the world in half the time.
Amazing.
Pretty good. Well, Aussie company Hypersonics is attempting to make that a reality, having successfully built a hypersonic aircraft prototype.
The Pentagon announcing this week that the U.S. has successfully completed 2 test flights of a reusable hypersonic aircraft, opening the door to more rapid development of arms that can travel more than 5 times the speed of sound.
America just flew a jet at a speed that, according to every aerospace textbook written in the last 50 years, should not exist in our atmosphere. Not in theory. In the sky, the engine should have melted, the airframe should have shredded, the fuel should have boiled before it reached the combustion chamber. Every known law of thermodynamics says what happened next was impossible. And yet the aircraft landed on an ordinary runway, refueled, and is scheduled to do it again. What you're about to see isn't a prototype or a concept, it's real.
The Pentagon says the U.S. needs to close the gap with China in terms of new-age missiles.
The DoD is now working with private companies to create new hypersonic aircraft.
And it changes everything we thought we knew about flight. The ceiling. No one could break for decades. The SR-71 Blackbird wore the crown as the fastest air-breathing jet ever built. A long, black titanium ghost that screamed across the stratosphere at over 2,190 miles per hour, more than 3 times the speed of sound. Nothing touched it. The Blackbird retired in the late 1990s, and the world more or less accepted that extreme speed in the atmosphere had hit its ceiling. Then, a small company in Atlanta decided to ignore that ceiling entirely. Hermeus was founded in the late 2000s by A.J. Piplica and a group of engineers who had already worked on real high-speed flight for the U.S. Air Force, SpaceX, and Blue Origin. Not dreamers writing grant proposals, people who had built things that actually flew.
New York to London in 90 minutes. That's the hyper-ambitious goal from hypersonic startup Hermeus Corporation. A small but growing aerospace player developing a family of aircraft capable of flying at 5 times the speed of sound.
They came together around one shared conviction. The wall everyone kept running into wasn't a physical law. It was an engineering problem, and engineering problems have solutions. Their target, a reusable aircraft that cruises at Mach 5, roughly 3,800 miles per hour, sustainably enough to carry passengers or fly repeated military missions. Not a one-shot weapon. A real aircraft that takes off, completes the mission, lands, and does it all again tomorrow. Here's what those numbers mean in plain English. Mach 1 is the speed of sound, about 760 miles per hour near sea level. Most long-haul commercial jets cruise at around Mach 0.85, a New York to London flight at 7 to 8 hours. Engineers reserve the word hypersonic for anything above Mach 5, close to a mile every single second. Hold that across the Atlantic and the crossing shrinks to around 90 minutes. Your coffee from the New York airport is still warm when you land in London. That's the vision. And here's what nobody in the industry wants to say out loud. Every serious attempt to get there before Hermeus melted, failed, or got canceled. The gap. No one talks about. While commercial aviation slowed down after the Concorde era, airlines chased fuel economy and got slower. The world's military powers sprinted in the opposite direction. Russia has been publicly demonstrating the avant-garde hypersonic glide vehicle, a warhead that rides the edge of the atmosphere at many times the speed of sound while actively maneuvering toward its target. China unveiled the DF-17, a ballistic missile that releases a hypersonic glider capable of skipping along the upper atmosphere, changing direction mid-flight, and staying off radar far longer than a conventional missile. These aren't exotic prototypes. They've been tested, paraded, and described openly as operational systems. The problem they create is brutally simple. The missile defense systems the United States spent decades building were engineered around objects that follow predictable arcing paths.
It is a 21st century arms race, and the United States is picking up speed here. Pentagon officials touting successful test flights of hypersonic aircraft, really helping the U.S. close the gap with our enemies and other global military giants.
A hypersonic glider maneuvering at Mach 10 doesn't. It flies lower, it moves faster, it changes course, and it arrives before defending systems have time to respond. But the deeper strategic issue isn't the incoming threat. It's the gap on the other side. A missile is a one-shot tool. It flies once, and it's gone. What American defense planners have publicly described as the real prize is something else. An aircraft that takes off from a runway, crosses an ocean in under an hour, executes its mission, and comes home to fly again tomorrow. Reusable, responsive, and fast enough that no existing interceptor can reach it in time. That is the gap Hermes was built to close. And before you hear how they're actually doing it, hit subscribe. This channel goes deeper into the machines reshaping the world than anywhere else on YouTube, and you'll want the next one in this series when it drops. Why physics says no. Here's the thing about going fast that most people don't appreciate. Speed isn't the hard part, heat is. When a spacecraft like Crew Dragon returns from orbit, it hits the atmosphere at extreme speed, glows white hot, and endures enormous thermal stress. But only for minutes. The entire design goal is to slow down fast. A hypersonic aircraft is the exact opposite problem. It can't slow down. It has to accelerate to Mach 5 and hold it for hours while carrying fuel, sensors, electronics, and eventually human passengers. Now look at what the air does at those speeds. It stops behaving like a fluid. The compression at the nose is so violent that the air itself heats up before it touches the metal, a phenomenon called aerodynamic heating. Temperatures on sharp leading edges at Mach 5 can exceed 1,000 degrees Fahrenheit, approaching what you'd find inside an industrial furnace. Aluminum melts. Even titanium begins losing structural strength. Seals burn. Fuel lines overheat. Standard electronics can't survive. This is why engineers in this field say the same thing almost universally. Hypersonic flight isn't a speed problem, it's a heat problem. And that heat problem has stopped nearly everyone who has seriously tried to solve it.
The heat facility here at Cecil will provide continuous flow conditions necessary to rapidly develop high Mach air-breathing engines. Heat will come online over a course of 6 phases, starting with sea-level static testing of the Pratt & Whitney F100 engine later this year.
Concorde proved passengers would pay dramatically for shorter flights, and that civil aviation could sustain Mach 2. It cut the New York to London crossing to about 3.5 hours. The airframe heated so much in flight that the entire metal structure grew several inches in length. Engineers had to build deliberate expansion gaps into the design, but Concorde burned fuel at a ruinous rate. Its sonic boom confined it almost entirely to ocean routes, and it carried only around 100 passengers at a time. After a catastrophic crash near Paris in 2000, it was retired in 2003. Mach 2, less than halfway to where Hermes is going. The SR-71 proved something different, that a crewed aircraft could survive near hypersonic conditions for sustained periods. Built largely from titanium, it flew so fast and so hot that the fuel tanks couldn't be sealed on the ground. The jet literally leaked fuel on the runway before every mission, and only stopped when the metal expanded in flight and closed the gaps. It needed specially developed fuel and a fleet of tankers just to operate. And even the Blackbird never reached Mach 5 in sustained level flight. 2 stairs on the same staircase. Concorde proved passengers would ride a fast jet. The Blackbird proved a crewed aircraft could survive extreme speed. Mach 5 in a reusable aircraft is the next step, and it still shouldn't be possible. Which brings us back to that test cell in Indiana. The impossible engine. Most people stop at the airframe when they look at a hypersonic aircraft. They see the sleek pointed shape and assume the fuselage is where the hard problem lives. It isn't. The real story is the engine hidden inside, a piece of engineering Hermes calls Chimera. Stay with me. This is where the impossible starts making sense. A conventional jet engine is brilliant from takeoff through modest supersonic speeds. Spinning turbine blades pull in air, compress it, mix it with fuel, ignite it, push exhaust out the back. But as the aircraft goes faster and incoming air gets hotter, those same spinning blades become a liability. At high Mach numbers, they can no longer process the airflow efficiently. Performance falls off sharply. A ramjet solves the high-speed problem by eliminating mechanical complexity entirely. Essentially, a shape tube, no spinning parts. The vehicle's own velocity rams air into the intake so violently that the geometry compresses it through aerodynamic shaping alone. Fuel is injected. Combustion happens. Exhaust rushes out the back. But here's the catch. A ramjet produces essentially zero thrust when the vehicle is slow. You can't take off in one. Chimera does both. At low speeds, it operates as a conventional turbine-based jet engine. As the aircraft accelerates, it transitions. Airflow is redirected around the turbine core into a separate ramjet duct, where combustion continues without rotating components. One engine, two operating modes. What sounds clean in a summary is, in physical reality, a controlled explosion inside a machine that cannot afford to fail, because the hard part isn't either mode, it's the moment between them. Hermias calls it the Valley of Death. Picture it. You're back inside that Notre Dame turbo machinery laboratory, late 2022.
And WSBT's Annie Chang joins us from the live desk now. Annie, you got a first-hand look at Notre Dame's aerospace engineering department, and they give us a better idea of what exactly will be going on in that new lab.
That's right, Rick. We heard Kelly mention this facility is all about turbo machinery. Big word. It's going to be used as a testing site for engine parts, and scientists will use it to keep testing and improving those parts so they can make the most fuel-efficient and safest engines.
Ground infrastructure around the test cell is forcing air into the intake at the equivalent of Mach 4. The engine genuinely believes it's in the sky. A row of consoles along the control room wall streams pressure, temperature, and flow rate data in parallel. One engineer's eyes are locked on the combustion stability trace. A second tracks mass flow. A third, standing behind both, holds the kill command. Everyone has agreed, quietly, on the exact reading that ends the run. Then the control sequence initiates the transition. For a fraction of a second, neither the turbine nor the ramjet has full authority. The turbine is winding down. The ramjet duct is opening. Airflow is being redirected in real time at conditions no conventional engine test has ever recreated on the ground. They're looking for three things at once: that the airflow doesn't stall, that combustion doesn't drop below the threshold needed to maintain thrust, and that the pressure readings don't spike in a way that would, in flight, tear the engine apart. Getting it wrong in the sky means the aircraft falls out of it. Over approximately 5 months of late-night test runs in 2022, the Hermias and Notre Dame team pushed Chimera through much of its planned speed range. They made it through the valley. The mode switch worked, from the plan to a confirmed repeatable mode transition. Under 2 years, on a budget of tens of millions of dollars. By defense acquisition standards, that is almost offensively efficient.
The test campaign marks the United States' first return to reusable hypersonic flight testing since the manned X-15 program ended almost 60 years ago.
But a mode switch that works on a test stand is not a mode switch that works at 70,000 feet. The next time Chimera has to do it, the ground won't be there to catch it. The heart of the machine. Here's where the story gets practical. The first version of Chimera used a General Electric J85 turbine core, compact, reliable, the right starting point for early learning. But Hermias always knew they'd need a stronger foundation for the aircraft that would actually chase Mach 5. So they turned to the Pratt & Whitney F100, the engine family that has powered F-15 Eagles and F-16 Fighting Falcons for roughly 50 years, delivering around 29,000 pounds of thrust in afterburner with over 28 million flight hours accumulated. One of the most battle-tested turbine cores ever built. And even that engine needs help surviving what Mach 5 does to incoming air. At those speeds, air arriving at the intake is hundreds of degrees Fahrenheit before any compression has happened. Fed straight into the compressor section, it would warp, crack, or destroy the internal components. The engine would eat itself. The solution is a pre-cooler, an extraordinarily dense heat exchanger positioned behind the intake. Incoming air passes through thousands of tiny channels packed tightly together, shedding thermal energy before it reaches the turbine face. A massive amount of heat removed in the fraction of a second the air spends transiting through it. Hermias plans to manufacture it from nickel-based alloys using advanced 3D printing. Think about what that buys them. Pair the pre-cooler with the F100, and the cooled air lets the turbine core operate at higher speeds and efficiency than it was originally designed for, pushing its effective speed range upward, narrowing the Valley of Death. Hermias runs combined pre-cooler and F100 tests at their ground facility in Jacksonville, Florida, a site called HEAT, for high enthalpy air breathing test. built inside former Navy test cells and upgraded with modern instrumentation. Owning the facility means iterating on the engine the way a software team iterates on code. A.J. Piplika describes the philosophy this way: build it, test it, break it, fix it. In an industry where engine programs span decades, that is almost radical.
Hermeus, founded by former SpaceX and Blue Origin alum, the three-year partnership turbocharges a plan to fly passengers commercially as soon as the end of this decade.
But the test stand can't fly. And until Chimera flies, none of it counts. That's where Quarter Horse comes in. The climb to Mach 5. You don't build a Mach 5 aircraft by starting with a Mach 5 aircraft. You build stairs. Hermeus organized those stairs under the name Quarter Horse, a structured progression of test aircraft, each designed to prove something specific and hand the knowledge to the next vehicle. In 2021, the U.S. Air Force and venture investors together awarded around $60 million to fund the series. The approach mirrors what made SpaceX disruptive: build the hardware, test it hard, accept failure, extract the lessons, roll them into the next version. The first vehicle, Mark 0, never left the ground. A full-scale structural mock-up used to validate hydraulics, fuel lines, wiring, landing gear, and the remote flight control architecture Hermeus calls the flight deck. Its job was to surface integration problems early when they're cheap to fix. Then came Mark 1, the first Quarter Horse built to fly, an unmanned demonstrator powered by a General Electric J-85 with a short, highly swept wing optimized for high-speed performance. Hermeus and the Air Force took it to Edwards Air Force Base in California, where virtually every major American record-setting aircraft has been tested. Late May 2025, first full flight. The remote pilot team at Edwards brought the aircraft to rotation speed and lifted off. It flew its planned test pattern. Control surfaces responded exactly as the computational models predicted. When it rolled to a stop after landing, one of the pilots exhaled slowly and said to no one in particular, "The math was right." 3 words. That's all it took to mark the moment an airframe shaped for high Mach performance had just proven it could take off and land from a conventional runway on ordinary landing gear. Non-negotiable if future hypersonic aircraft are going to operate from standard bases. Box checked. Next stair. Quarter Horse Mark 2.1, roughly the size of an F-16, unmanned, powered by the Pratt & Whitney F-100, that will eventually integrate with Chimera's full combined cycle system. In early March 2026, Mark 2.1 took off from Spaceport America in New Mexico for its first flight, using restricted airspace over White Sands missile range, designed to exceed Mach 2 as testing progresses.
Spaceport America in southern New Mexico, our state's big money gamble that was supposed to be a sure payoff. Back in 2010, the legislature was battling a budget shortfall, but still approved $200 million to build the spaceport.
One of the fastest unmanned aircraft ever flown, and all of it is the warm-up for Quarter Horse Mark 3, the first vehicle planned to carry the complete Chimera, 2-engine, and attempt the live mode transition from turbine to ramjet in actual flight. Take off under turbine power, accelerate through supersonic, close the turbine flow path, open the ramjet duct, keep accelerating. If Mark 3 does that cleanly in the sky, it will be something never achieved in a reusable aircraft. A door that has never been opened. What Mach? 5 unlocks. Speed only matters if it does something real in the world. 2 applications define what Hermeus is building toward, and they sit at opposite ends of the spectrum. Start with the defense side. It's called Dark Horse, a reusable hypersonic drone designed exclusively for military missions. An unmanned aircraft approximately 45 feet long, targeting Mach 5 using the same hybrid engine architecture as Quarter Horse. Unlike a missile, it flies the mission, returns to base, and flies again. Picture what that changes operationally. Instead of a reconnaissance aircraft spending hours approaching a defended coastline, trackable, predictable, vulnerable, Dark Horse lifts from an ordinary runway and sprints to its objective at several thousand miles per hour. It can cross a body of water the size of the South China Sea in well under an hour, execute its mission, and exit the threat envelope before air defenses mount an effective intercept. The speed itself is a form of protection, but the real power is what you can pack into a single fast pass. A dark horse sortie could map radar installations along a coastline, identify which systems activate in response, and relay that intelligence in real time to assets hundreds of miles out. On the next run, the same aircraft might carry electronic warfare equipment to suppress those systems during a follow-on strike. Now, flip the coin. The second application changes the civilian world entirely. Hermes calls it Halcyon, a roughly 20-seat hypersonic passenger jet targeting Mach 5, approximately 4,600 miles of range, focused on long overwater routes, New York to Paris in around 90 minutes.
Today, we've got so much better technology. We've got aerodynamics, materials, propulsion, computer-aided design that are just light years ahead of where we used to be.
Ticket pricing aimed at the premium business class market. Halcyon would cruise at altitudes approaching 90,000 feet, nearly 3 times higher than a conventional airliner. Up there, through the window beside your seat, the sky doesn't look blue anymore. It fades to a bruised, almost black violet. For the first time in your life, you can see the gentle curve of the Earth bending away at the horizon. Stars visible in daylight. The Atlantic a silent sheet of hammered steel 90,000 feet below. One regulatory obstacle sits outside Hermes's control. Since 1973, the United States has prohibited routine supersonic commercial flight over land because of sonic booms. Any hypersonic airliner would face the same. Restriction, confining it to ocean routes unless regulations change. NASA and Lockheed Martin's X-59, designed to reduce the sonic boom to a soft thump, made its first flight in late 2025. If regulators are persuaded, overland restrictions could be relaxed. Halcyon would benefit directly. Hermes isn't alone in this race. Stratolaunch has already flown its Talon A reusable hypersonic test vehicle beyond Mach 5. In Pentagon-backed trials, the Talon A-2 was dropped from a carrier aircraft, lit its rocket engine, exceeded Mach 5 over the Pacific, and landed at Vandenberg Space Force Base, the first reusable American hypersonic test asset since the X-15. But a speed record is not a sustainable aircraft program. Europe's reaction engines spent more than 30 years developing its Sabre combined jet rocket engine with a sophisticated pre-cooler, genuinely groundbreaking technology, before running out of funding and entering bankruptcy in late 2024. The engine never flew. That's the cautionary tale hanging over everyone in this field. What Hermes has that reaction engines didn't is hardware that has left the ground, a funded Air Force partnership, and a methodology that generates flight data instead of analysis. Quarter Horse is flying. Chimera has demonstrated mode transition on the ground. Mark 2.1 is already in the air. The SR-71 held the speed record for nearly half a century. The aircraft that breaks it next won't just be faster. It will take off from an ordinary runway, cross an ocean in the time it takes to watch 2 movie trailers, execute its mission, and come home to fly again. No rocket, no throwaway stages, no launch infrastructure, just a plane, a runway, and a speed the textbooks still say isn't supposed to be achievable. If this story makes you feel like it still shouldn't be possible, good. That feeling is the point. Every stair Hermes climbs is a stair 50 years of aerospace. History said didn't exist. So, here's the real question. One morning in the not-too-distant future, a business traveler boards a 20-seat aircraft at JFK, orders a coffee, opens her laptop, and 90 minutes later, that same coffee, still warm, touches down in Paris. She doesn't clap. She doesn't film it. She closes the laptop because she has a meeting at noon, and Mach 5 has become the boring part of her Tuesday. When that morning arrives, will you believe it happened? Or will it still feel somewhere in the back of your mind, like something that shouldn't exist? Drop your answer in the comments. I read them all. And if you want to be there when the next impossible breakthrough lands, subscribe. We're just getting started.